Okay, we are going to apply the concept of what's called the differential. So let me write it out like this: dy equals f prime of x dx. We're going to apply this concept. Suppose that you might also see it like this. I don't know. But we're going to use these kind of things interchangeably. Now, here in this general form, you see x and y. When you look at the application problems, you're not going to want to use x and y. You're going to use the variables that are given in the problem. So let's take a look at number 5, and then I think you'll start seeing that how you're going to make the connection to this stuff over here. All right. So let's take a look here. Problem number 5, and let me kind of make this a little bit bigger for you. Let's see if we can still keep that formula in there, right about there. That looks good. All right, so we have a equals pi r squared. We know to be the area of a circle, where r is the radius in centimeters, and it says by approximately how much does the area of a circle decrease when the radius is decreased from 2 centimeters to 1.8 centimeters, and then it says use 3.14 for pi. So what we're doing is we're looking at two quantities, and I'm going to call them dA and dr. All right, dA is the change in the area, and dr is the change in the radius. So what was the initial radius that they gave us? Well, it's this right here, 2 centimeters. And we're going to jot all of this down. So let's go ahead and do that first. I'm going to say, well, my initial radius is 2 centimeters. All right, what is my change in the radius though? My dr, or my delta r in this case. Well, it went from 2.0 to 1.8. So there's my dr, okay? It's 0.2 or 2/10, if you will, okay? So I'm going to use that, and then what I have to do is differentiate. I have to take the derivative. So the derivative of a is what we're just going to call dA or delta A. And then of course r is the variable, and we're going to say 2 pi r and then dr. Okay, this should be very reminiscent of like implicit differentiation, or kind of like a related rate. All right, that's why this probably in your textbook or whatever it is you're studying, it came right after that section. Okay, so we've got that down, and now all we have left to do is plug in the information that we were given. And so we know that r is 2 centimeters, so that's going to go plugged in right here. And our delta r, our dr, is 0.2, and that's going to go plugged in right here. And then the rest is easily computed on a calculator, if you will. So let's take a look. What is dA? We're going to get a numeric value here. 2 times pi times the radius of 2. The change in the radius is 0.2 centimeters. So we end up getting centimeters squared, because 2 centimeters times 0.2 centimeters, there's your centimeters squared. So this is by how much the radius will be reduced. You do that computation, you get something really close to 2.5 square centimeters. All right, so this right here is your change in the area. So the question was, by how much does the area of a circle decrease? Well, it decreases by about 2.5 square centimeters. So that's what that problem looks like right there. Okay, and we can do one more problem. This one's a little bit more challenging, but it's all the more fun when it's challenging, right? So let's take a look at this next one. Again, we're going to continue doing this kind of approximation, of course. This one a little more involved, a little more intense, only because the derivative we have to take is just slightly tougher. It's the quotient rule, if you will. So let's write that down, okay? Let's remind you what the quotient rule says. And I always use this kind of little mnemonic, or this little song. I always think of the 7 dwarfs. I say low d high minus high d low over low low, which is the bottom squared. And this, of course, is high, and this, of course, is low. And that's what we're referring to when we take the derivative of some rational function, if you will. So we're going to need to do that. So let's go ahead and write down what it is that we know. We know our function c of x, right, is 7x over 14 plus x squared. It says use the differential to approximate the change in concentration. So this says the concentration of a certain drug in the bloodstream x hours after being administered is approximated by this function. Use the differential to approximate the change in concentration as x changes from 1 to 142. So my initial x value is 1. Okay, so I'm going to write that down. That's important. But my delta x, or my dx, is given by the fact that 1 goes from 1 to 1.42. That's the change in the, what was it again, hours. So my delta, my dx, is 42 hundredths. Okay, all right, so 42 hundredths. There's my dx. Now all I have left to do really is take the derivative and then kind of plug in some stuff. And so I know that they say, oops, that jumped there. I know that they say c of x, but what we're going to be looking for is, well, we're going to look for c prime, I suppose, but we're going to look for dc is what we're looking for. That's what we're computing, of the differential for the concentration, dc. So we shall first find, let's say, c prime of x. And in order to do that, let me write down what I know. High is 7x. Low is 14 plus x squared. D high is 7. D low is 2x. And I'm going to find my c prime now. My derivative, low d high. So I have 7 times 14 plus x squared minus high d low. So let's say 7x times 2x, all divided by low, which is the bottom, the numerator, I'm sorry, the denominator, quantity square. Okay, and you can clean that up. You distribute. What is 7 by 14? 98. 98 plus 7x squared minus 14x squared, all divided by the denominator, quantity square. You can yet again combine like terms. 98 minus 7x squared divided by 14 plus x squared, quantity squared. Okay, you get something that looks like that. And then of course you write dx. Okay, so when we're looking at this dc value, we know we're going to plug in 1 for x. And we're going to replace dx with our delta x that we computed back over here, 0.42. So let's see what that looks like. 98 minus 7 times 1 square over 14 plus 1 squared, and all of that quantity square, times my dx, which I calculated over there at the beginning to be 0.42. So let's see what this works out to be. Do a little bit of order of operations. 98 basically minus 7 is 91 divided by, and then 14 plus 1 squared is 15. 15 squared, 225. Not 222, 225. Okay. And then I multiply that by 0.42. Of course, you're probably going to want a calculator for this one. What is that? Approximately like 0.1698 or something like that. But how about this 0.17? All right. This is your DC, which is the differential to approximate the change in concentration of this drug treatment in the bloodstream. So really nice application of differentials. It's more than just that initial formula that we went over at the beginning and that maybe we went over in another video. There's applications for this kind of stuff. So it's actually quite interesting. So I hope these examples were helpful. And as always, like and subscribe.